let's look at this notion of independence and correlation. As you know, independence is when the joint density function is the product of the marginal density functions. Now, when we another notion is the expected value of a function of two random variables. It's actually whatever is the function multiplied by the joint density function. And of course, if x and y happens to be independent, then this formula doesn't really simplify, but of course here you can replace it by the product of the density functions. Where this is a little more useful is, suppose this the function also happens to be the product of two different functions of x and y. So expected value of gx hy would be, in general of course it would be gx multiplied by hy multiplied by the density function, but in this case if x and y are independent, then you can write the this as fx x fyy dx dy. Notice that this integral has split up now, separable variables. You can separate the variables. So consequently, we can write it as the expectation of x multiplied by expectation of gx multiplied by expected value of ghy. So this is an interesting simplification, and I'm going to use this to show you certain things on this correlation. Okay. So let's take x and y to be independent. Then we can also define the concept of covariance between x and y is expected value of x minus mu x multiplied by y minus mu y. By the way, this is the covariance, this is the definition for covariance, whether it is independence or not. But notice that it splits into two functions. So if x and y happens to be independent, then this is the product of the expected values. Product of the expected value of this multiplied by this. So if x and y are independent, of course you can see the covariance is 0, because it's the expected value from here is the product of the expected values. And similarly, the correlation coefficient is the actually normalized correlation coefficient is the covariance between x and y divided by sigma x, sigma y. No, normalized covariance. So of course, if the numerator is 0, and then correlation also 0 in this case. So we are just talking about the case where x and y are independent. What we have shown is the correlation is, so covariance is 0, correlation is 0. So we can write that if x, y are independent, then their correlation coefficient is 0. So we call x, y are uncorrelated random variables. And you can see that there is no reason to believe that it will be true the other way. So in general, this is not true. What I'm trying to say is that if two random variables are uncorrelated, they do not have to be independent. How do you show this? Best way is show an example. So uncorrelated doesn't mean independence. Except, of course, there is a exception, except when x and y are jointly Gaussian. So how do you prove that case, the last case, the jointly? So just write down the density function for fxy jointly Gaussian means, remember, it's some constant e raised to minus 1 over 1 minus 2 rho squared. Here, I'll take the zero mean case. So this is sigma x squared minus 2 rho xy sigma x sigma y plus y squared over sigma y squared. Now, of course, if they are uncorrelated, means the rho is 0, that's what we mean by uncorrelated, then you can see that this simply becomes the density function of x multiplied by density function of y. So we have actually proved that this is true starting with from here. So if the theorem is independence, of course, it implies uncorrelated for all random variables. And uncorrelated in general, of course, does not imply independence, except when x and y are jointly Gaussian. So to make sure that this is true, what you need to see is construct an example where the two random variables are uncorrelated, but then show that their joint density function is, they are not independent. In other words, the joint density function is not the product of the density functions. You can find several examples in book, but once you get the idea, you can try to create your own example.